Scott misses playing soccer and the trumpet in these COVID times, but he will now talk to us about a common error creates competition between parallel sensorimotor learning systems. Take it away, Scott.
Everybody, thanks very much for coming to the talk wherever you may be in the world. So to begin, I'd like to start off by saying the brain is exposed to a perturbation that it has experienced in the past. It learns more rapidly the second time it sees that perturbation. And this is something that we refer to as savings, and it's a hallmark of learning. So you can see this when you adapt walking movements, eye movements, reaching movements, even in classical conditioning paradigms for the eye, and even in the cognitive domain, which is where the term savings has been borrowed from. And the central question in motor learning is, what are the memory systems that are supporting the brain's ability to increase its rate of learning? So in 2015, Adrian Heath and colleagues did an interesting experiment where they had participants move a cursor through one of two targets. And when they moved the cursor towards target 1, the cursor was rotated relative to the direction they moved their hand. This is a perturbation that subjects adapted to over time. And on most trials, participants had a lot of time to prepare their movements. They're shown a target, and then they reach towards that target, and they are allowed a second and a half to prepare that movement. And at these high preparation time trials, what the authors observed was savings. So when participants were exposed to the perturbation twice, they learned more rapidly the second time, which you can see here in this blue curve, and you can quantify the rate of learning just with an exponential. But on a subset of trials, on about 20% of trials, participants actually were forced to move with low preparation time. So on these trials, they were shown the target, and then they had to move within 300 milliseconds after having seen the target come on the screen. And in this case, importantly, what they observed was that there wasn't any savings. There was no difference in the learning rate expressed at low preparation time during the first to second block. And so this begs the question, of course, what is the difference between high preparation time trials and low preparation time trials? And I don't have too much time to go into this, but evidence points to the idea of explicit strategy, so that when participants are shown a perturbation and they're provided a lot of time to prepare their movements, they can intentionally and explicitly try to counteract the perturbation. But these cognitive strategies require additional time, additional processing time for their expression. And so when you suppress them, you are highlighting these more implicit subconscious corrections that are readily available to you. And so what these data suggested is that savings relied on this time-consuming recall of explicit strategies, but implicit systems that were available immediately didn't exhibit savings. And this may be obvious, but it's really important that when we're thinking about savings, that when we're trying to compare learning in two different environments, that the driving force for adaptation has to be the same in those two environments to correctly compare the rates of learning. And so what we're going to talk today is, what is the driving force for adaptation? And so we're going to talk a little bit about what drives adaptation in these implicit learning systems, and how actually, depending on which errors you believe drive implicit learning, actually affect how you interpret savings in these types of tasks. Okay, so in these tasks, participants reach towards a target. And as I just discussed, they are free to re-aim their reaching direction. So they see a perturbation and they decide, oh, I'm going to aim someplace else. That's going to reduce my error. But so there's an explicit component to adaptation. But on top of this explicit component, the brain has subconsciously learned things about past errors. And so it is implicitly recalibrating these reach directions, such that the direction you actually move your hand is really the sum of two components, an explicit component and an implicit component. Then there's a rotation that moves the cursor relative to your hand, which creates an error. And one of the errors that the field often talks about is a target error. And these target errors is the discrepancy between where the target is and where the cursor goes. And this is the error that you would need to minimize in these tasks in order to achieve success. But there's another type of error that is also of very central interest. And these are called sensory prediction errors. So in a normal case, when you are reaching your hand towards a target and you're aiming to this target, you would expect to see a cursor go towards where you're aiming. However, in this case, the cursor goes off in a different direction. And so there's an error in prediction. I predicted the cursor is going to go where I aimed it, but the cursor went over here, and there's now this sensory prediction error. So two different potential sources of error, and they're actually really different from each other. And the reason for the difference is the following. So if you just mathematically express what a target error is, a target error is contributed by the rotation, the perturbation you experience, but it's also altered by both your implicit and your total amount of explicit adaptation at any moment in time. The sensory prediction error is different, though. The sensory prediction error is tethered to where you aimed and therefore doesn't depend on the aiming direction. It actually only depends on the rotation and the implicit amount of adaptation. And so these two different error sources actually make very different predictions for how the implicit system should respond to a perturbation. Okay, so to understand these different predictions, we consider these state-space models, which are these really simple models we use in the field to try to track adaptation. So here, these models describe how a state of adaptation X here changes between two trials. And there's two processes. There's the forgetting process, the first term here, and that's controlled by one's retention factor A, or a forgetting rate. And the second is learning from error, which is controlled by this error-based learning from here, which is controlled by one's sensitivity to error, which we call B. All right, so what we're going to study is the behavior of these models over long exposures to a perturbation after the system has reached a steady state and implicit and explicit systems have equilibrated. So in the case where implicit systems are learning from target error, we saw that the errors depend on both implicit and explicit states of learning. If we combine all these different pieces of information on this slide and do a little bit of algebra, we can show that theoretically speaking, the total amount of implicit learning in this case should be driven by this following function. The right side of this function is a driving force for adaptation. This is what causes the implicit system to adapt, and that is the perturbation R, and discounted by any explicit strategies the subject is using. The leftmost term is just a gain that varies between 0 and 1, and this gain is just determines how strongly people respond to the driving force for learning, and this gain depends on implicit learning properties. So what about in the case where the implicit system adapts not to a target error, but to a sensory prediction error? Here we know the error depends on implicit state. And so if you just do the algebra again, what you can see is a very similar equation for steady state learning. The learning gain is exactly the same, but critically the driving force for adaptation is different. If people learn from a sensory prediction error, it's the perturbation that's driving adaptation, independent of any explicit strategies. And so this is the really critical difference between these two types of errors. And so how do we determine which of them is driving implicit learning? So in this experiment, participants are adapting to a 30-degree rotation, and the learning curve is shown here as a function of trial. And we also measured reaction time on each trial. And what you can see is that when the perturbation turns on, reaction time sharply increases. And this is very typical. And this is generally consistent with the fact that participants are observing a perturbation and trying to come up with explicit strategies to respond to that perturbation. So when we try to isolate implicit learning, what we often do is we'll strict reaction time to try to suppress these explicit strategies to prevent people from using them. And when you do that, you can see that learning occurs more slowly and it's less complete. And so potentially this memory that's shown here in the black curve is an implicit memory. We want to understand its learning properties. Okay, so again, we have two equations. If the implicit system learned from a sensory prediction error, its total amount of learning should be described by this equation. And I'm going to call this the independence equation because this equation only depends on the perturbation and it's independent of explicit strategy. But if the implicit system is learning from a target error, it is learning based on a competition equation. The competition equation is affected not only by the perturbation, but also is competing with an explicit strategy. Okay, so we can specify these linear equations by just empirically trying to calculate what error sensitivity is and what this retention factor is. I'm not going to go into the details here, just dig in time, but in this experiment 2 here, we measured the implicit retention factor and we also measured the implicit error sensitivity. And now you can specify these equations and you can make predictions. So the sensory prediction error equation predicts that implicit adaptation will be about 23 degrees or so, and that's independent of any explicit strategy that someone might have. However, if they learn from target errors, it's still the case that the implicit system is depending on how much explicit strategy there is, and so we have to measure that. So at the very end of experiment 1, what we did is we told participants to reach their hand straight through the target without using any re-aiming strategies. And so as you can see, when you do this, adaptation drops off very significantly. And the drop in adaptation is the conscious component of adaptation that people have control over. This is their explicit corrections. And the remaining amount of adaptation is just this implicit system that you don't have conscious control over. This is just a subconscious correction. And so if you take this explicit adaptation here and you plug it into this equation, you make a different prediction for how much steady state implicit learning should have occurred in experiment 1 here. And so now we can test these two predictions against each other. And to not belabor the point, what we found is that the total amount of implicit learning measured in the presence of explicit strategies was consistent with competition, but wasn't consistent with an independence from explicit strategy. Now you could also make these predictions not across participant groups, but from one subject to another, right? Because this equation right here predicts that subjects that have larger explicit strategies will have smaller amounts of implicit learning. And so this is actually a line in this space where you plot implicit versus explicit reach angles. And that line is given by this equation, which we specify with experiment 2. And now we're looking at data from experiment 1, every individual subject. And what we found is that the actual measured correlation subject to subject between implicit and explicit learning agreed very well with these theoretical predictions. Okay, so another experiment that also demonstrates these interactions between explicit and implicit learning is by Neville and Pressman in 2018. And so here participants adapted to a 40-degree rotation. And then a separate group of participants were told about that rotation ahead of time. They're told about the rotation and how they're going to compensate for that rotation. And what you find is that when you instruct the participants a priori, they learn more rapidly, which isn't so surprising. And this happens when you do a 40-degree rotation, a 20-degree rotation, and also a 60-degree rotation. And so the critical difference between these two things is how the explicit system is responding to, in this case, rotation magnitude. And so the explicit components get larger and larger as the rotation gets larger in size. In addition, there are, how does the explicit system respond to instruction? So unsurprisingly, when people were instructed about the perturbation, they learn more in terms of their explicit strategies. Okay, so how do all these differences in strategy affect implicit learning? Okay, so again, if the implicit system learns from a sensory prediction error and it responds to the perturbation itself, what you would predict is that awareness doesn't affect the implicit learning system at all. It should learn the same amount independent of instruction. But if you learn from target error, as you instruct and you get larger explicit strategies, implicit learning should go down. And this is what the model would predict. And the data look something like this, again, consistent with the competition. Okay, you could also look at how the implicit system responds to magnitude, right? And so if you learn from a sensory prediction error, your total learning will scale with the perturbation magnitude, just linearly, like this. But if you learn from a target error, the driving force is not the perturbation, it's the difference between the perturbation and explicit strategy, which also, as we knew, increased with the perturbation size. And so the competition equation actually predicted that learning is pretty similar across each of these rotation sizes. And the data were actually more consistent again with competition and not independent adaptation. Okay, so brief summary before I get to my last point I want to make here is that the data suggested that implicit and explicit systems responding to the same error, and that this shared error couples these systems together and leads to competition. And so lastly, how might these interactions between these systems affect our ability to detect changes in implicit learning properties, so savings? So here is that savings experiment I started off with coming full circle. And what we wanted to know is if we fitted a model where both implicit and explicit systems adapt to target errors, what does this model predict in terms of how savings is occurring? So we fit the model to block 1, we fit the model again to the second block of adaptation. And what we found, unsurprisingly, is the model predicted that the explicit system during the second exposure became more sensitive to error, became more vigorous in its response to error, which wasn't surprising. However, the model also predicted that the implicit system had also become more sensitive to error on the second block. And this was surprising. It was somewhat confusing because if the implicit system became more sensitive to error, why on low preparation time trials do you not measure any change in the rate of learning? And it turns out that this unintuitive situation is actually explained by competition. So during block 2, when explicit strategies are expressed very rapidly, when these strategies come online really rapidly, they're siphoning errors away from the implicit system, which is decreasing the driving force for implicit adaptation in the second perturbation block. But what we found is that the implicit system learned at the same rate. And so the model can only account for this seeming contradiction by saying that it believes in response to these smaller error sources that the implicit system must have increased its implicit error sensitivity to maintain a similar rate of adaptation. So if this is true, the key prediction is that if we completely suppress explicit strategies and get rid of all competition with explicit learning, that will unveil implicit savings. Okay, so this is the data from the Hayth experiment, where strategies are suppressed on only 20% of trials, and we don't see savings in the implicit system. What we did here is that we suppressed explicit strategy on every single trial. And in this case, we found that on the second block, there was savings, that during the second exposure to the perturbation, the rate of implicit learning increased, which is suggesting potentially one interpretation is that implicit savings is unveiled by the suppression of explicit strategies, which are masked by competition for error. Okay, so just to summarize really quickly here, in these experiments, I've shown you the subjects were moving to a single target, and the implicit system appeared to be primarily engaged by task errors. And this error was also shared with the explicit system. That led to this competition. When explicit strategy increased, it took errors away from the implicit system, and that led to less implicit learning. And that this competition may mask changes, our ability to detect changes in the implicit learning system. Now, what I didn't have time to talk to you about, what is actually really critical to know, is that these learning rules don't apply for all experiments exactly this way. It seems that the implicit learning rules are flexible. So I described tasks here where people move to a single target on a screen. And in this case, it seemed that that one target generated primarily one source of error. However, in other versions of this task, people see multiple visual targets, or visual targets can move. And what this actually seems to occur during these tasks is there's multiple error sources that engage the implicit system simultaneously, which unfortunately I didn't have time to show you evidence for this. But it seems in these cases that there's both a task error and also an aiming error that both engage the implicit system. So just to summarize, the implicit system appears to exhibit a flexible response to error, which is altered both by context, which I didn't really get into too much, and these explicit strategies. Okay, so just want to thank everyone else on the team working with me. And I don't know if there's any time for questions, but I'd be happy to take any.
So we don't have any time for questions as we have to get to Carly, but you do have